chair this session entitled Research and Academic Opportunities from Megahertz to Terahertz. From outside, I think it's difficult, right, to understand what it means to pursue a career in academia, which are the skills required, which is the impact that you can make. I think that today you have the really unique opportunity to hear the experience from 4 distinguished speakers, professors and educators who lead some of the most well-reputed and advanced research groups in the world. Let's start with the first speaker, Professor Zoya Popovic from the University of Colorado, Boulder. She is a distinguished professor and Lockheed Martin Chair of RF Engineering at the Department of Electrical, Computer, and Energy Engineering of Colorado Boulder. And she has graduated over 70 PhDs and currently advises 18 doctoral students. So thank you, Zoya, for being here, and the floor is yours.
Thank you very much, Valentina, and thank you all for inviting me. It's really a pleasure to speak to such an incredibly global audience. I don't think I've ever done that before. So this is a really fantastic opportunity. I will tell you about snippets of our research, and I'll try to illustrate it, telling you where the different students find employment and how we get to the projects that we get to work on. So hang on just a second. So you might be wondering, where is Boulder? It's not an MIT and it's not a Stanford. Boulder is located in the middle of the United States. Well, not in the middle, roughly 2/3 between the East and the West Coast, closer to the West Coast. And if you live in the United States, it turns out that the universities are ranked in different groups. And the Tier 1 research university group are the top research universities in the United States. And what you can see here is that most of them are concentrated on the East or the West Coast, and the middle is completely empty, and we're the only school in the middle. And what that means is that there are a lot of smart kids everywhere. People live in all these empty spaces here. And so I'm very fortunate to get amazing students that come from the empty looking states on the map. Here, the blue are public schools and red are private institutions. So what does it look like? You know, we've got some mountains here. These are the Rocky Mountains. Boulder is at 2,000 meter elevation. And we have 32,000 students. We have 5 Nobel Prizes, 4 in physics and 1 in molecular biology. Very well-funded university. In fact, we've been the largest NASA-funded university in the US for the past 20 years. The main campus is in Boulder. It's a city of about 100,000 people and about as many bicycles. I'm fortunate because we have a lot of national institutes in this area. One is NIST, is the National Institute Standards of Technology. And an example of that is that the world time is kept in Boulder. Actually, I can bike in 5 minutes to the cesium fountain clock that keeps the world time currently. There's also NREL in the neighborhood, which is the National Renewable Energy Laboratory, and that's the Department of Energy, and also a bunch of institutes that take care of weather, National Weather Institutes, as well as the United States Geology, USGS. So it's a very lively place to do research in. At my university, I'll skip a little bit about the other details of the university. We have a great physics department and a lot of other very good departments. I'm in the College of Engineering and in the Department of Electrical Engineering. Our RF group has 4 regular faculty, and then we have some research faculty and some other people that we collaborate with. And these are my colleagues, Professors Filipovic, Barton, and Scarborough. And we also have a research professor, Laila Marzal, and 2 other faculty that we work with heavily. And I'm, sadly or not sadly, the oldest one. So we cover all the areas that normal suspects for microwave engineering: antennas, active circuits, some filters, front ends for comm and radar, remote sensing, and computational electromagnetics. We have over 50 PhD students among us and are well funded, and we've been fortunate to be recognized by our peers with a number of awards. So what enables research at the US university, at least, and I'm sure that you'll hear that it's similar in other places as well. Well, number one is we don't really get any support from our university. In fact, we pay to our university to do research in the form of overhead. So if I write a proposal to one of these agencies or companies, a student generally costs me about $120,000 a year. That covers the student's salary, tuition, benefits, meaning health benefits and all that, as well as $56,000 of that goes to the university to cover things like lighting and laboratory space and so on, as well as some of my time. So these logos that I'm showing here are government agencies such as the Office of Naval Research, Navy Crane, DARPA, and so on. This is an energy office. There are also institutes such as MIT Lincoln Labs, which is also a government institute, NIST, which is Standards and Technology. Some companies, some are large companies that you may have heard of, some are small, very small companies, and then other government organizations such as the National Science Foundation and NASA. And this belongs to the Department of Commerce. So that's yet another, government kind of body. So the other thing we need is university infrastructure. So that means labs and a space to live in. And my university has really been great. I've been here 34 years. So this is the end of my 68th semester as a professor, which is a very depressing number, actually. You need industry partnerships. And I'll talk about that in a moment. It's impossible to work in a vacuum. So collaborating with people around the world and at your own institution has been really important for us. If you don't participate in your professional institutions, you also cannot be successful in research, in my opinion. And even if you don't work with some companies, it's really important to communicate with industry, and that has to do with student employment later. And then finally, the most important thing are students. So when I talk about infrastructure and industry also, I mean labs as well. And we're very fortunate, for example, some of my colleagues that are on this call actually have much better labs than we do, but we have a lot of companies and institutes that we can work with. And that's why these collaborations are so important. Win Semiconductor and Corvo are very strong collaborating companies. And then I encourage everybody to be active in the IEEE. It's a great society. And without it, I don't think we'd be here for sure. So students are the most important thing for me because that's my product is a person. And it's very important that my students are really experts in their field and that everybody wants to buy my product, which means hire my students. So student recruiting is incredibly important. And I'd like to thank all of my students who have been doing phenomenal work over the years. These are various generations. We go on field trips to big antennas, so I'm showing a Recibo, which sadly doesn't exist anymore, Mauna Kea and the VLA. And then the bottom right picture is my group did a surprise birthday party for me when I turned 60, and they all showed up in my backyard, 70 some of them. So that was really a very special day. So it's all about these young people who will carry us forward. Actually, my oldest student retired, which is very depressing. So I'll give you a current research overview and touch on who we're working with in the different ones. So generally, in terms of topics, as Valentina said, I have 18 PhD students now, and so they all have to work on different projects and have to have different theses. So some of them are working in MMICs, so microwave integrated circuits in 3-5 semiconductors. We don't do silicon, and you'll hear more from other speakers on work in silicon. We're interested in high efficiency power amplifiers for communications and radar. And we're also interested in pushing the envelope to higher frequencies, but obtaining higher power at higher frequencies, and also integrating with not just amplifiers, but integrating with other parts of analog front ends. I've also over the years done a lot of work in microwave powering, and that remains a small part of my research. And some of it has been extremely interesting, and I might show you a slide about that. generally it's about arrays, whether they're near field arrays or far field arrays. We do other kinds of antennas, broadband efficient transmit arrays. These are for jammers. We're also very interested in self-calibration for simultaneous transmit and receive arrays, which is, in other words, better use, for example, of the electromagnetic spectrum and being able to do simultaneously functions such as radar and comms. And related to that, one needs to worry about interference suppression. Most of it can be done digitally, but it turns out if you have a broadband front end, that analog methods are really very useful. There are a lot of medical applications of microwaves, and I'll touch on one of the projects that we're working on. And finally, there's a new popular word called quantum. And it turns out that a lot of the atomic transitions are in the microwave frequency region. And so quantum physicists and quantum engineers really need help from microwave people. And this is not a new thing. Actually, my group has been working on quantum devices for a very long time. I will not talk about this that much because there's a lot of different explanations and introductions one needs to do. But if somebody's interested, I'd love to be able to comment on it. So let me start with the first topic that I discussed, and then I'll give you a little snippet from the others. So the problems in microwave transmitters. First of all, transmitters, you will hear people say that the power amplifier in a transmitter consumes most of the power in a radio system. That's not actually always true. It depends on the power level. But for example, in a satellite, about 40% is consumed by the PA. And sometimes it's even hard to find numbers, because people implement things differently. But generally, the transmitter consumes a lot of power and heats things up because it's not perfectly efficient. And the problem is that as you cram more data into a radio link, the signal tends to have a modulation that varies in both amplitude and phase. And so the amplitude variations, this is the envelope of a signal. So that's the modulation. The carrier is like the black stuff inside. It's very, very high frequency, right? So the envelope might be something like a few 140 to 100 megahertz, let's say. So as the amplifier of the transmitter is moving between these low and high amplitude levels, the efficiency really changes. And the efficiency of a traditional amplifier is very high when you're at high power levels at these peaks, but you're not there very often. The bars show the probability density function of the envelope. So the problem is that in average, your efficiency will be very low. What you'd really like is this green curve. And so there are a number of methods that people use for that. Another challenge is that once you operate an amplifier efficiently to conserve your power, then the amplifier will tend to be very nonlinear. And so that means you'll get a lot of distortion in the signal. That in the spectral domain, it means that you'll pollute maybe an next door neighbor. And there are many metrics. This is a different metric. It's called NPR that's used to characterize the linearity. And finally, a third problem, and there are a lot of other problems. I'm just illustrating three. That is that the load might vary over time. And so if you have a cell phone, you may put it next to your head or put it on the table, and that will present a different impedance to the antenna and therefore to the amplifier. And similar things happen if you have a phased array and you steer the beam, the reflection coefficient at the amplifier port actually changes. And you can put a circulator there to prevent that, but circulators are bulky and people don't like them because they have magnets. And so that's another interesting problem. I will not be able to talk about all of these, but just so you know, we have projects funded by various people in all of these challenges. So I'll show you just one. We use a lot of gallium nitride now. Part of it is that that's what people want to fund. So you have to be pragmatic in this business. Sometimes you really would like to do something else. For example, I think gallium arsenide is a fantastic semiconductor, and it does a great job at many applications. But it's kind of old news. And so gallium nitride is currently a very promising semiconductor. It does have a lot of issues as well. But there's a huge benefit, and the benefit is in power. So what you see here is our two chips. They're both Corvo chips, so formerly Triquint. One is gallium arsenide, it's the big one, and one is gallium nitride, the smaller one. And they have the same output power. at Ka band, and they're very different size. And that immediately tells you that gallium nitride has a much higher power density. And that comes from the fact that you can operate it to a higher voltage. And so it'll give you a higher power per millimeter of a chip. And that's a big advantage. The other advantage is that actually it's made on silicon carbide most of the time. And that's a very good thermal conductor, better than gallium arsenide. And so it turns out not only can you get the power out, but you can also get rid of the excess heat. So I want to talk about efficiency enhancement because heat is usually what limits a lot of systems. For example, a phased array in space for satellite comm is thermally limited. So there are a few ways that people have been doing efficiency enhancement, and this is old news, and I'm sure my colleagues will talk about this as well. But basically, they include adding another amplifier. So instead of taking one microwave amplifier and then operating it in back off if you're worried about linearity and then just having to deal with the excess heat power, what you can do is add another amplifier. So for example, the Doherty PA, and my colleague Christian Fager, who'll talk to you later, is a real expert in this. It's in all base stations now, as far as I know, and it contains two amplifiers. One takes care of the kind of lower power levels, and the other one takes over when higher power levels are pushed through the amplifier. And this is an excellent architecture. It has some drawbacks like bandwidth and so on. I'm sure Christian will tell you more about it. Another one is outphasing. It's again, you have two amplifiers and you do something with the phase at the input, enabling each one to be efficient all the time. And a third one is supply modulation or envelope tracking, where actually the second amplifier is not an RF amplifier, but rather very fast dynamic power supply. And so I'll tell you a little bit more about that. We've done all of these. The pictures that you see here are pictures of X-band MMICs that, just a moment, excuse me, Mama. I'm sorry, my mother is visiting and she was making some noise in the background. So I wanted to tell you more about these chips. I won't tell you about all of them, but I'll show you some examples. These are all X-band gallium nitride MMICs that implement these different architectures. There are also others, like a load modulated balanced amplifier that many people are working on right now that enables bandwidth. People have also done interesting harmonic injection amplifiers. They all need at least one additional amplifier. So the question is, you know, if you need this additional complexity, is the added complexity worth it? Am I winning because my efficiency is so much higher now of the main amplifier, but I've added all this other stuff? And so that's an important thing to say. So I'll give you an example of a supply modulated amplifier that we've used for very high peak to average ratio signals. This is an amplifier made in the Qorvo GaN 15, so 150 nanometer process. It's on silicon carbide, and we've used a nonlinear model made by a small company, Modulated. This is an example of an industry collaboration. 3 ways. So Qorvo is a foundry. They also have excellent design engineers, and some of them are my students. So this is an employer, for example, for my students. They have a government group where US citizens are hired, but they also have groups that don't require citizenship that do gallium arsenide. Modalytics is a small business. It's another company that we work with a lot. And they make nonlinear models as well as linear models for surface mount components, and their models are really outstanding. So this amplifier is relatively old, you know, it was 12 watts at the time at 10 gigahertz. It's a narrow band amp, about 20% bandwidth. It has a very high efficiency. The bottom curve shows measured efficiency as a function of output power for a variety of drain supply voltages. So what you see here is that if I operate at a 20-volt drain supply, for example, then most of the time, if I have a signal that varies in power, most of the time, I will be in a very low efficiency region. And so what I can do is change, when I'm at a lower power level, I can change to a different supply voltage. This one is 8 volts, for example. and keep my efficiency much higher. This is many percentage point improvement. And you know, heat actually scales non-linearly with efficiency. And so this is a huge improvement in thermal dissipation. So only if I had a dynamic power supply that could change at the bandwidth, or actually turns out much faster than the bandwidth of my signal, then I can keep the amplifier cool. And so the next question is, can I get such a supply? The answer is you cannot buy one, so you have to figure it out and you have to make one. And so this shows two different kinds of IC, so gallium nitride supply modulators, we call them. So these are these very fast dynamic supplies. And one is a collaboration. We made the chip, and we designed it, but it was a collaboration with a group in Bologna in Italy. And these are fantastic colleagues. I've learned a lot from them. And it was very important for us to be able to communicate and to collaborate. Another one is a collaboration inside my university with Professor Maksimovic, who is actually an expert in power electronics. And this is an incredibly efficient, very fast buck converter, which is a dynamic kind of a power supply. And so I just want to stress how these collaborations are critical. Without them, we wouldn't be able to integrate this amplifier with the dynamic supply and obtain a very high efficiency. In fact, one of the Italian colleagues sent me a student who was a postdoc, now he's a professor at Villanova University, Tommaso Capello, and he demonstrated that by integrating this amplifier with this power supply, we were able to get a total combined efficiency of 55% on average for an OFDM signal, which is a huge improvement in thermal. Okay, so these are some other measurements. I won't go into detail, but I'll tell you that this approach also lends itself to quite broadband signals, but then you actually have to deal with some nonlinearities. And so what we found is something very interesting, and that's that you can use some analog linearization at the front end by varying the gate supply instead of doing digital pre-distortion, which is difficult for very broadband signals. And we've been able not only to improve linearity, but it turns out we also got an improvement in efficiency. So this is an example of how, you know, people want to do everything digitally, but it turns out there are a lot of really useful analog techniques that one should keep thinking about because it helps the digital downstream. And this was, again, a collaboration with the University of Vienna, where a young man, I was on his committee, and he came and did a postdoc with me, and now he's a professor at Chalmers with my colleague Christian Fager. Gregor Lasser is his name. The other students are currently employed they were at SpaceX and at Northrop Grumman. So one can scale this to a higher frequency. This is just an example of a K-band amplifier for satellite phased array. My understanding is that Lockheed Martin is currently flying these chips on one of their phased arrays. So that was very cool for my student to see. In this case, there were 3 stages. It was more broadband. These are measurements from 11 chips that you see here. And you can see a power added efficiency that exceeds 40% is in most of the satellite band, with a good output power and very good saturated gain. So I work also with very close colleagues. Professor Taylor Barton, for example, she gave a talk in a workshop yesterday that I understand was very well attended. And an example of that collaboration is that one can include a little mini network analyzer, if you want, in a chip. And that's implemented. Her student, Devin Donahue, who is now working in a local, actually small satellite company called Cesium Astro, designed this sampled line, sort of a reflectometer, if you want, a network analyzer, and he integrated it inside the matching circuit of an amplifier, which I thought was really cool. And then he worked with one of my students, Philip Zurich, who is now at MIT Lincoln Labs, and they integrated this on a chip and made a 9 and 16 dual band gallium arsenide mimic that had an ability to actually measure the impedance presented at the output port. So if the antenna changes, you would be able to adapt this. So that's another very interesting area of research. We'd like to scale this to higher frequencies where there's more bandwidth. And so this is an example of a W band PA. This means this power amplifier works from 75 to 110 gigahertz. This is implemented in the HRL laboratories 40 nanometer gallium nitride process. This is a phenomenal, really high-end gallium nitride process, and they're very fast. We get chips in 3 to 4 months from this. And you can see that we're able to get over 25 dBm measured power. The efficiency is pitiful, but this is a very broadband and very high frequency amplifier. So we were quite happy with these results. And you can integrate this in a bigger front end. And what this shows is a full front end that will be coming out shortly in the MTT transactions, done by my student Tim Sonnenberg, who just went to join Corvo, Tony Romano, who just graduated last week, and I don't know where he'll be working, possibly at NIST. They integrated a full balanced power amplifier that you saw on the previous slide with a gallium nitride switch, which turns out is unbelievably linear. In fact, with a watt output power out of this PA, we were not able to saturate the switch. And then there's a 4-stage LNA at the bottom. And so it's a full TR front end that reaches 1 watt output power in the low part of W band. That's a photograph of the chip that you see here. And some performance that maybe not that exciting right now, but I'm supposed to be finishing up soon. So I'd like to show you a few other things. So once you make these chips, you may want to integrate them with other kinds of chips. So the word for that is heterogeneous integration. And the idea is that you take, for example, gallium nitride that's very good for power, gallium arsenide that's good for noise, and then you take CMOS to control everything, and then you need some good passives. So we've done integration in HRL process called MECA, where you flip these chips, you fill back with a lot of copper, so you have a really good thermal and RF ground and DC ground as well. And then you get rid of the substrate that you flip them on, so all the chips are planar, and then you can deposit, you don't have to bond wire, you just deposit these metal interconnects. And when you do that, because of the good thermal ground, you can get an amplifier that actually has an improved efficiency because the heat sinking is better, so the gain goes up. And we've done better than if you tested on a probe station, say. We've done other kinds of integration. This is done with Corvo, a collaboration funded by the US Navy. And it's to have an interposer that's silicon with 6 metal layers, 3 on top, 3 on bottom, and a polymer, so organic layers. And this just shows an example of how we've designed a through interconnect between those layers and its performance out to 50 gigahertz. And that was done by these excellent students who are still working with me. So we also do phased array. I'm going to finish up now, but just give you a glimpse of some other projects just so that you know what kinds of things people are interested in funding. So this shows an active broadband array with some amplifiers, and then we've also included some analog interference cancellation, because when you have a very broad bandwidth, you're opening yourself up to a lot of interference. And so you have to take care of that. And digital has a hard time actually with dynamic range in that case. And so we help it with some analog interference cancellation. The biomedical application is to measure internal body temperature. And there are many applications for this, from arthritis to overexertion to actually surgical applications in open heart surgery. And you can use microwaves actually to non-invasively measure internal body temperature by using radiometry. And that's another interesting example with which I'll finish of working with a small company. Actually, we had a patent in this. This shows an example of one of our circuits. And what you see here is a probe that is designed to be placed on the temple, on the forehead during cardiac surgery. And a company, Lumenastra, has licensed this patent and was formed around it and is now commercializing this technology. And while we're shrinking it and making things a little better, and since you can't put a hole in the brain to measure the temperature to check if your measurement is correct, what we do is do measurements on the cheek, and we put hot and cold water, and we can track the temperature instantly at the speed of light through tissues. So other projects I won't talk about. This is a picture of various rectangular arrays that we've done. And I'd like to thank you for your patience. And I hope I'm in time. I've been trying to monitor, Valentina, but we started a little later. So that's.
Thank you very much, Zoya, for this very interesting review of your research activities. I have a couple of questions that I got from the audience.